Hello and welcome everyone. I'm Peter Robinson and this is the Ethereum Engineering Group Meetup. Today we've got Roberto and Thanh-Hai who are going to talk about the distributed validator protocol. So before we dive in, Roberto and Thanh-Hai, why don't you introduce yourselves?
Sure. Hi everybody, I'm Roberto. I work for Consensus, specifically I'm in Consensus R&D in a team that uses formal verification applied to distributed protocols to analyze the security, and we are mainly currently focused on protocols as they relate to the Ethereum blockchain. Over to Thanh-Hai.
Thanks, Roberto. Hi, everyone. I'm Thanh-Hai, and I also in the same team with Roberto, and I focus on formal verification of distributed protocols. Yeah, it's me.
Okay, cool. Well, welcome. So I'm interested to. You'll probably tell us when you dive into the talk, but how does this distributed validator protocol relate to Ethereum 2? Or should we just watch the, you'll do the talk and you'll tell us?
Yeah, it's probably, let's leave this question to the end. Let's see if it gets answered.
Okay.
Yeah,
all right, over to you.
Thank you. So the agenda for today is to try to answer to 5 key questions. One is, why do we need a distributed validator to start with? Then why do we need to formally specify and verify the distributed validator technology protocol? How does our formal specification look like? How does our formal verification look like? And finally, what we've actually been able to achieve so far and what is in further ahead in our plans. So let's dive directly into the first question. Sorry, before I do this, there is an acknowledgement I need to do. This project is actually supported by a grant by the Ethereum Foundation, OBOL, and SSV Network, and was done by Consensus R&D. So let's dive into the first question. Why do we need a distributed validator? Well, let's look at how a normal Ethereum validator, which we call centralized Ethereum validator, and the reason why we call it centralized will be clearer sooner. So an Ethereum validator, as you can see, is composed by the architecture is usually splits it into a beacon node and a validator client. However, this is not really a distributed architecture. Architecture is just a separation. It's actually, this architecture is subject to a single point of failure, as beacon node and validator client play 2 different roles. And problem that you can have are software bugs, network failures, or power outages, just to mention a few. And also you have another problem, which is that the key that is held by the validator client can be hacked. So an hacker can potentially steal the key. And we'll see soon in the next slide what this means. So let's have a look at, okay, it's basically now we know that this is a system that can fail. There is no redundancy if you want to it, but let's look at what the consequences are. Let's look initially at the problem of having an unresponsive node. So we have the blocks at the top. They symbolize the slot in an Ethereum protocol, and P is a slot where a node is supposed to propose block. A is where it's supposed to create attestations. In the Ethereum protocol, the entire time divided into slots. For some slots, one validator is chosen to be the proposer, and a set of validators is chosen to be basically voting for the current head of the chain. So when everything is okay, when it's our turn to propose a block, the Ethereum validator is alive, it proposes a block to the Ethereum network, and therefore it gets rewarded for that. Similar, when it's the turn to create attestations, the Ethereum validator create attestation, submit them to the network, it gets rewarded for it. Now, assume that the Ethereum validator fails. So any of the two components, for example, I showed you before, fails. What's going to happen is that when it's our turn to propose a block, well, we don't do that. And therefore, we don't get any reward. Worse is when it's actually our turn to create attestations. So we failed, we don't create attestations, which means that we missed the reward, but we also incur penalties because we didn't create an attestation. So the consequences of having a failure in the node is that we can miss the rewards and we can also incur penalties. And now let's look at what happens actually in the case that the validator key is compromised. One thing before diving into it, I want to remind that in Ethereum, there are two types of keys. One is the withdrawal keys, which is used to withdraw when this will be available to potentially withdraw the stake. Another one is the signing key, which is used just to sign attestation. So let's assume that just the validator key is compromised, not the withdrawal key. In this case, what can happen is that the malicious node can sign two attestations that are slashable. We'll see later what this means, but let's assume that basically they are violating some fundamental rule of the protocol. And the node can then create a slashing proof, can package all of this into a slashing proof using their own key. So using the malicious validator key to sign the slashing proof, submit this to the network. As a consequence of this, the honest validator gets slashed. So basically, some of their stake gets taken away, and some of this stake is actually transferred to the malicious node. So in a way, even though the malicious node does not steal the withdrawal key, it's still capable of taking some of the funds away from an honest node and increase their own balance. So these are the two main consequences of what can happen if an Ethereum validator fails or the signing key is stolen. Now, one might think of a solution, just simple solution, which is let's run multiple validators so that we have redundancy. Okay, we still don't solve perhaps the problem of the validator key being stolen, but at least we have the redundancy. Well, this is perhaps what someone did at the beginning of when the Ethereum Beacon chain was launched, but this proved not to be a correct solution, as this is actually almost the right recipe to get slashed, because if these multiple validators instances, they don't communicate with each other, they can create conflicting blocks or node or attestations, which then causes them to get actually slashed. This is what the distributed validator technology protocol addresses. This is the problem. And to be clear, this is a protocol that was, we didn't design it, was designed by the Ethereum Foundation. And the basic idea is to create a middle layer here, which is called distributed validator, which is represented by the distributed validator clients, which connects the beacon node and the remote signer. The remote signer, you can think of it as an equivalent of the validator client I showed you before. The only difference is that the remote signer accepts requests to sign a block or an attestation, whereas the validator clients do that on their own. They don't accept requests to sign, they just send signed blocks and attestation because of the architecture of the protocol. In this case, there was a need to replace validator client with remote signer, but they basically fulfill the same role, which is to sign blocks and attestations. So essentially what we have is that we have a distributed validator signing key, and this is split into different shares. Each share goes to a different signer, and then we have the distributed validator protocol, which is responsible for coordinating the various components and making sure that the overall system is seen as a as a validator. And essentially, this is, if you can think of this as a, so the component of DVT are threshold signatures, a consensus algorithm to get agreement and to coordinate everything, put together with additional logic to fulfill the requirements of the protocol. So let's look at the different components. As I mentioned, we have threshold signatures. But the role of the way threshold signatures come into play into the protocol is that where the validator signing key split into n shares, and these n shares can be used to reconstruct the signature as if it was signed by the original validator signing key. One of the properties is that you need at least m out of the n shares in order to be able to reconstruct a valid signature. As long if you have less than m, you can't. Basically, or it's highly improbable that you can construct a valid signature. And this is what essentially provides key theft resilience to the protocol. We'll see later how this interplays with the overall protocol. The other component that we have is a consensus algorithm, which is in this case is a Byzantine fault tolerance consensus algorithm, which means that it can operate correctly despite less than 1/3 of the nodes potentially being Byzantine. And the main property is that this consensus algorithm has to ensure agreement, validity, and termination. So agreement is depicted on the right-hand side. You can see 4 nodes. One is malicious. The objective is that all the honest nodes, they reach the same decision, despite the dishonest node trying to confuse them. The validity property is says that there is some validity condition on the decided value, and the protocol must ensure that any decided value satisfies these validity conditions. And termination says that the protocol must eventually any honest node must eventually reach a decision. Now, in the DVT protocol itself, it's kind of agnostic of which VFT protocol is used, and as long as it satisfies these properties. In a way, the idea here is that people can choose different protocols, perhaps protocols that work under different conditions, as long as these properties are satisfied. So I just want to give a brief illustration of how DVT works in the case of attestations. So in Ethereum, in the Ethereum validator world, we have the concept of a duty. A duty is something that is created at the beginning of an epoch. And an epoch in the Ethereum protocol, we have, as I mentioned before, the time is divided into slots, and every 32 slots, you have a new epoch. So at the beginning of an epoch, a new duty is created. And this duty basically says when the validator is supposed to create attestations and what its position in the committee of validator is. And this index is something that must be included in the attestation that is created. So, okay, we have a new epoch, a new duty is created. When it's the time for the validator to create a new attestation, what the different distributed validator client composing the distributed validator do, they communicate with the consensus layer to start a new instance. And of course, the malicious node might try to start earlier, might try to start later, as it doesn't necessarily follow the protocol. What's going to happen then is that the consensus protocol ensures the property we saw before and performs as this performs attestation validation on whatever is decided value. Eventually, a value is decided. So basically, because all the honest nodes reach the same decision on which is the value of the attestation that needs to be created. At this point, each distributed validator client signs the decided value with their share of the sharded key, and sends this decided value together with the signature. It broadcasted to all the nodes in the network, and this is what in the distributed validator technology protocol are called attestation shares. Now, these honest nodes, they don't need to follow this. They can try to send attestation shares before, they try to send them later. Of course, they can try to disguise the other nodes to try to get to the wrong conclusion. Now, once a honest node receives enough attestation shares to be able to reconstruct the signature, can reconstruct the signature and can create and submit an attestation. And each node can do that. And the idea here is that even though we can have multiple attestations created, they will be the same. So there is no issue in terms of being slashed. Now let's look briefly at what are the expected behavior of the distributed validator technology protocol. We have a property about safety. So again, safety, when we speak about safety in general, we want to say something bad never happens. That's high-level concept. So one property that it's important for the distributed validator technology protocol is that a distributed validator staking private key is secure unless security is compromised at more than 2/3 of the distributed validator clients. Another property is that a distributed validator never commits slashable violation unless more than 2/3 of the distributed validator clients are Byzantine. And okay, there's an error in the slide. It should be more than 1/3 of the DC are Byzantine. So this condition is guaranteed in this case under full network asynchrony, meaning that we allow any possible message delay. So message delays are arbitrary. So we consider message might be delivered immediately, never delivering in 10 seconds, 100 seconds. We allow any type of schedule. And liveness says that a distributed validator eventually produces new valid attestations and blocks. And this is proven under a different network condition, or this must hold under different network condition, which is a synchronous network, meaning that message delay is bounded and known. So before I hand over to Thanh-Hai, I just want to close this section talking who actually benefits from this protocol. Well, of course, we have stakers, so stakers staking products and staking pools, but most importantly, the Ethereum protocol itself. This is because the Ethereum network is only as secure as Ethereum validators operated by honest participants. And the reason for this is that the security of the Ethereum protocol relies on the fact that 2/3 of the stake is in honest hands. However, if honest participants are hacked and their stake can be slashed, or even worse, some of the portion of the stake can be diverted to malicious participants, then this balance starts to tipping over towards more favorably towards malicious nodes, and therefore decreasing the security of the network. Okay, now I'm ready to hand it over to Thanh-Hai.
Hi, Roberto. I think the section, why do we need to formal verification and specification, is on, you want to present it on me?
Okay, I can do this one. Okay, so why do we need to, okay, asynchrony. Why it is important to formally specify and formally verify such a system? Well, the good news about this is that we have removed any single point of failure, and therefore we have a higher resiliency. However, we've also increased the complexity, which means that we also increase the chances of design bugs. So how can formal verification help us? So I just want to give you a feel about this and compare formal proofs to testing, which is a technique commonly used in software products to try to reduce the chances of errors. So the overall key takeaway is that formal proofs are exhaustive, whereas testing is not exhaustive. So what does it mean? Let's look at the network size considered. With formal proof, we can consider any network size, any number, finite size, you name it, we can potentially build a formal proof that shows that the system guarantees certain properties against that size. Whereas for testing, we need to use more sizes. Otherwise, the testing time taken by the test is going to grow exponentially. Also, in terms of Byzantine behavior considered, we can consider any type of Byzantine behavior. Any type of Byzantine behavior means that we can code it. Of course, we exclude things like changing an honest node states, but we don't have limitation in the terms of specifying what the type of behavior we want to specify. Whereas in testing, you can only deal with simplistic Byzantine behavior, like for example, on a node stopping or sending conflicting messages, but you need to pick and choose the type of Byzantine behavior you want. Also, if a given property is not true, through the formal proofs will be detected. Basically, we will never be able to put together a formal proof that checks. Of course, it's up to the experience of the people putting together formal proofs to actually reach a point where they understand that there is a problem, but at least you will never get to the point where you think that something is true, but it's not true. And whereas in testing, all your tests might pass, but the property might still not be true. And if the property is true, through formal proofs, we can prove it. With testing, we cannot prove it. We can only show that whatever is the test case, all the test cases passes, but we cannot generalize this property to all the possible cases. So let's look briefly at what formal verification consists of. We have a formal specification, which is a mathematical definition of the behavior of a distributed protocol, which essentially says when message X is received, that message Y should be sent. We also have a definition of the properties that we're interested in. And this again is a mathematical definition of the properties that the protocol is expected to guarantee, like never commit a slashable offense, for example. Altogether is linked by a formal proof, which is a mathematical proof that the protocol specification guarantees the property is defined. Now, what we want to do, we want to take this a step further and have proofs that are machine checked. So proofs that are checkable for correctness by a computer, which provides higher degree of confidence in the correctness of the proof. And this is what we target with our work. So concluding my section, it's time for real. Our target is to have formal proofs of the safety property against slashing. So we want to show that a distributed validator is never slashed, can never be slashed as long as less than 1/3 of the distributed validator clients are Byzantine, and we have a threshold signature scheme and a consensus algorithm that work correctly. And we can do this by verifying two sub-properties, which is one is about the fact that honest distributed validator clients never submit slashable attestations and they never submit slashable blocks. Now I can hand it over to Thanh-Hai.
Thanks, Roberto. So I guess that everyone can see my screen. And now I'm going to show you how our formal specification looks like. And instead of a big single file, we want to split our formal specification into smaller files. And here you can see that on the slide, there are many boxes, and each box becomes one module in our specification. The first box is about distributed validator. So this spec describes the behavior of a global system. It's a conjunction of the behavior of submodules. Here we have 4 submodules: network, consensus, adversary, and correct node. In our model, the network is asynchronous. And for the module consensus, we don't specify the details, the algorithm. We only assume about the properties that a consensus algorithm needs to satisfy. And in our model, the failure nodes are Byzantine. So it means that a Byzantine node can send different messages to different nodes, and they can behave as they want. However, a Byzantine node cannot create a signature from other node, and it cannot modify the state of other nodes. And correct node here is for honest node that follows an algorithm. And we have N is a number of nodes, and F is the number of failures. In addition, we have one more module that is for executable reference implementation of correct nodes. And our specification is written in Daphne. Daphne is a programming language, and its syntax is very similar to C or Python. Therefore, it's very easy for developers to understand the code written in Daphne. Moreover, Daphne is designed with a formal verification away. And let's start from the executable reference implementation. This is the code in Daphne for a method called attestation consensus decided. And you can see that this code is very similar to C or Python. So I guess that everyone can understand what is written in this code. And there's something new in this code. For example, here you can see that we have 2 keywords requires and modifies after the method declaration. And the developers can ignore these keywords because they are only used for formal verification purpose. In addition, we have operator for exception propagation at the bottom of the slide. And now I'm going to show you how our distributed validator formal specification defines a transition, a move in a system. So first, we need to define the initial state. The initial state is a conjunction of many states for submodules. Here we have the initial state S0. This is the global state. And we have N-F states for honest nodes. And we have another state for the network, one for adversary, and the last one is for consensus layer. And the next thing we need to specify is system transitions. In our specification, we can move from one state to another state by using the event. An event can be a new set of duties, or this is when a node needs to execute some duty, or when a message is delivered. Importantly, our formal specification captures non-deterministic behavior. In our model, there are two sources of non-deterministic behavior. The first one is about more than one event can be triggered in one state. For example, here you can see that if we are standing at a state S, so then from state S, we can move to state S prime or S double prime by using two different events. The first one is that node 1 receives message X from node 2, and the second is that node 1 receives message Y from node 3. This feature allows us to capture the behavior of a network. And the second source of non-deterministic behavior in our model is from the same event can lead to more than one state. For example, here we have an event that officially sends message S to node 2. And why this event can lead to different states? The reason is about the behavior of Byzantine node. So a Byzantine node can send different messages to different nodes. And now I'm going to show you more details about our specification written in Daphne. Assume that we have a transition from state S with event X, and now we can specify this transition by defining a function dv next event whose return value is Boolean. And we can move to state S prime from state S because in this function, we have dv next event S, event X, S prime. I mean, it is evaluated as true. However, we cannot move to state T because its evaluation is false. Now let's look at the Daphne code. So the first thing we have is a transition for on each node. This is the predicate node next. And we have three more predicates to represent the transitions for network, adversary, and consensus. And the conjunction of this predicate that presents a transition of a global system. And here you can see that we have quantified variables like message received, message sent, and decided value. And because there are many values for these variables that can make this predicate become true, so that's why we have a non-deterministic behavior. And in our specification, there are some part that we trust and another part that we don't trust. So you can see that here, the behavior of network, consensus, and adversary, they are what we trust. And also the definition of properties. However, we don't trust the behavior of single node, and also we don't trust the reference implementation. And in our work, a manual proof is not enough, so that's why we want to check our proof with Daphne. So this is a formal proof. And how can we increase the likelihood that what we trust is correct? We apply 4 following steps. First, we keep trusted specification part as simple as possible. So the number of code lines for trusted parts is very small compared to the part of non-trusted. Moreover, we apply the peer review to have the feedback from other researchers. And the tool we use, it has a strongly support for formal verification. The last step we apply is to formal proof both safety and liveness properties. And the formal proof will highly reduce the chances of errors in our assumptions. So let's consume a scenario that a network is completely crashed, so then no messages are delivered. And it means unit nodes cannot make any step. So it's very easy to see that in this case, the safety property is guaranteed. However, we don't want to have this scenario in our application. So by proving liveness, something eventually happens, something would eventually happen. So it means that every honest node we eventually can publish an attestation. So by proving the liveness, we can avoid unexpected scenario. And now I'm going to show you how our formal verification looks like. So the first thing we need to do in our proof is to formalize axioms. The axioms are for the behavior of our trusted path. So for example, here you can see two axioms. They are related to threshold signature functions. In Daphne, we specify the axioms by using two keywords, lemma and axiom. And the first axiom is a property of the hash root function. So it means that if the hash of two data, D1 and D2 is the same, so D1 must be D2. The second axiom says for every root, every signature S1 and S2 and one public key PK, if we can verify that a signature of D S1 and PK and also a signature of D S2 and PK, so it implies that S1 must be S2. Another thing I want to mention here is that for the axiom, so they don't have any lemma body. So in our proof, we use native invariance. And here I want to show you the definition of an inductive invariant and why we need to use an inductive invariant in our proof. So you can see that from an inductive invariant provides an over approximation of reachable state. Here, for example, we have an initial state, and from this state we can go to other states. But this set of states is the subset of states satisfying inductive invariant. And our proof has three steps. First, we show that in it, the initial state implies inductive invariant. And the second step, we prove that if the current state satisfies an inductive invariant, so then the next state must satisfy an inductive invariant. And the last step is to show that an inductive invariant implies a safety property. Sorry. So by using an inductive invariant, so we only need to reason about two consecutive states and also for an initial state. So this will help us to simplify the proof a lot. And the next thing in our proof is about quorum intersection. So in the DVT protocol, there are two important redstones. The first one we have is that 3 times f plus 1 is less than or equals to n. And f is the number of folds and n is the number of nodes. And the second question is about the quorum. A quorum is a majority of nodes, and we need to have at least 2n/3 of nodes in the quorum. And we have an important observation that given two arbitrary quorums Q and Q prime, we know that each intersection contains at least one unleashed node. And before showing you more details in our proof, I want to remind you about the definition of non-lashability for attestations. So our target is to prove the safety property against lashing for attestations. And to do that, we need to prove for every pair of attestations A and A prime submitted by an unleashed node, A and A prime are non-lashable. The definition of non-lashability is technical, and you can find the definition in the link before the image. Here, I just want to show you some intuition of lashing conditions. So we have two cases, the two conditions. The first one is that a validator cannot publish to different votes with the same target height. This is in the left picture. And the second condition is that a validator cannot publish a vote in the span of each other votes. And now I want to remind you about the construction of an attestation. So the step one is that a consensus instance needs to decide an attestation data for an attestation duty. And the data must be validated by all nodes in some quorum. Second, after knowing attestation data D, so then nodes need to send attestation shares with their signatures and the value of D. The final step is that an attestation can be constructed by a quorum of attestation shares. And this is the sketch of our core proofs. So we assume that an unleashed node DVCN submits to attestations A and A prime, such that A is submitted before A prime, and when to prove that A and A prime are non-lashable. So how can we do that? So let's look at the timeline diagram. So in this diagram, we have two important events that are submissions of A and A prime. And let's see what happens before the submission of A prime. So we know that to submit A prime, a decided data D prime of A prime must be decided by some quorum Q prime. And moreover, the RAM or this data, D prime, must be validated by all nodes in Q prime. And now let's look at the submission of A. And because to submit A, an unleashed node N needs to have attestation shares for A from a quorum Q. And if we make an intersection of Q and Q prime, we know that there is an unleashed node W in both Q and Q prime. And because W in Q prime, so we know that W validates A prime. And moreover, because A is submitted before A prime, so we know that an unleashed node W, it must know the value of A when it validates A prime. So then, because W is unleashed node, so we know that A and A prime, they are not lashable. Yes, this is the catch of our core proofs. So now Roberto will present what have we achieved so far and what is left to do. Roberto, please.
You tonight. So we are the last section of the talk. Let's start by speaking what actually we're able to do by October 2022, which is when we presented initial work at DevCon. So what we're able to do was to have a proof of this non-slashable attestation property, and using various assumptions. Most of these assumptions we've already mentioned them. One that is we haven't mentioned so far is that this property holds even if the beacon nodes or the distributed validator client, the beacon nodes connected to the distributed validator client are on different fork of the Ethereum chain. And I'll explain a bit more later what this means. And we are also able to prove that the reference implementation is a correct implementation of the specification. However, there is actually a liveness issue with this protocol. Not that we have proven liveness, but by reasoning about it, we saw that about this issue. And the issue is that what we had in this version that we kind of formally proved around October 2022 is that each distributed validator client had a queue of duties. This is because a similar scenario where there is with the current duty to be acted upon, and you also have a queue. Now, when a new duty is when it's the time to act on a new duty, for example, create a new attestation, assume that the consensus layer is still busy. What we were doing, we're not changing the current duty and queuing the new duty in a queue. And then once the consensus layer reaches a decision, we're popping a duty from the queue and serving that one. However, what is the issue with this scenario? Well, assume that we have a chain, and at some point we have a fork, not in the non-finalized part of the chain. And assume that we have 4 validators, 2 validators are on one side of the fork, 2 validators are on the other side of the fork. And this is the same situation where the new epochs done. At that point, the new duties are created, but because there are two different chains, the commit index for the same validator could be different in the 2 different forks. And the value of the commit index is something that is checked by the validation performed at the consensus layer, which means that basically you end up in a situation where the consensus never terminates, and because we are using a queue, we're waiting for the consensus to terminate before acting upon a new duty, you end up in a situation where basically no new attestation will ever be produced. So the way this was fixed, it was with this version 2. So we don't have a queue anymore. When we have a new duty, and for example, the consensus layer is busy at the time when a new duty is time to be served, what we do, we just start a consensus instance of the new duty. So we don't wait for the old consensus instance to finish. And of course, this doesn't create the block situation I told before, but it was important to actually prove that the non-slashable attestation is still correct, and that's what it does. So we've updated the format specification and reference implementation with this new to implement this new protocol. We have updated the proof of non-slashable attestations for the new spec. We've also written the format specification and reference implementation for the part about signing blocks. What is left to do is to update the proof that the distributed attestation reference implementation adheres to the specification, to do the formal proof for non-slashable blocks, and also to do the proof for liveness. And this is the last one. Thank you.
So,
Do you want to go to the next slide before the questions with the talks?
or we could do questions now. I can see Frank's got two questions in the chat. The first one was asked early on, and then the second one was later.
Okay. I'll answer them in opposite order. So, is there a reason to use for all post conditions instead of using parameters in the lemmas, into the axioms? Not really. That's we chose to do in that way. Just to present the lemma we could have done with the parameters. Personally, I find that sometimes having the for all allows to have a shorter proof. Sometimes is counterproductive, as actually Daphne never terminates, and having the parameters helps Daphne verifying things quicker.
Yeah, so that was actually my point. If you have a universal and quantified formulas, you may not be able to get through, whereas with parameters, if you know when you need to apply it, it's much easier.
Yeah. What I think what we end up doing is that then we have a lemma using this for all to have parameters, I think, to do exactly what this. So that the question, I'm not sure. I think it refers to one of the initial slides.
Yes, slide 11.
11. Okay, so when the decision is made, the decision is made on the idea is that we expect the consensus protocol to ensure is that the same value will be decided, and a property of the threshold signature scheme is that unless you have m out of n signature for the same value, you cannot construct the signature. Does it answer the question?
So it doesn't matter which subset of
no,
the validators submit. They submit. They don't submit actually something that depends on the parameter or the number of valid, the identity of the valid validators within the distributed validator.
Oh yeah. Okay. I think the dependency comes into play when the key is split between.
Yeah. So that's
keys.
that's the sense of my question.
Yeah, that's what happened. But that splitting is not. It's something we assume happens outside of this protocol. So
Okay.
we consider that the key splitting has already happened, and the nodes already have their shares, and that algorithm is correct.
Ron, do you want to ask your question next?
Thanks. I've got a couple of questions. I mean, one is relating to the actual representation that you're using of the crypto. Are you using sort of term algebra, or are you going deeper than that into sort of the representation of the crypto?
Oh, what we do, for example, we assume ideal crypto. I don't know if this answers your question, but for example, for the hashing, Thanh-Hai showed you, for example, we assume ideal hashing. So that the two hashes are the same. That means that there is we assume no collision, for example.
Yeah, so I'm worried specifically with respect to the structure of the messages that the Byzantine nodes might be cooking up. And it's very typical in reasoning about cryptographic protocols that your adversary might be sort of cutting bits out of messages that have gone across the network, composing together in complicated ways. And do attacks based on that sort of constructing of messages that end up deceiving the good players. So you're doing any of that sort of representation? Or does that not come up?
No, so not in this case. So we allow for, let's say, if there was a message containing multiple signed messages, we would allow Byzantine validators to reuse this signed messages inside a more complex message, but we just, in this case, we assume that Byzantine actor is not able basically to send a message signed by an honest validator unless it has already received it. That's kind of the assumption we rely on.
Mm-hmm. Okay, so then the second question relates to, you're doing this in Daphne, so I'm just wondering how you're representing an arbitrary number of nodes in
yeah,
which has some complicated code attached to it. So it's
we basically have it as a parameter on when we instantiate on the yeah, it's a
each of your proofs is for a fixed number of nodes.
It's for a finite number, any finite number of nodes. So we have what we have is
it just me, or has everyone lost audio from Roberto?
No, I think
it's just you. Yeah.
So we have what we do in the initial state, we pass a configuration parameter, which contains the number of nodes in the system. And our proof, we let that number be any integer. Don't know if this answers the question.
Mm-hmm. Okay.
And then we use basically for all, like we have a lot of for all statements to say something is true and for all then honest nodes, for example, in the initial set.
I say basically that an environment object which is representing the states of all of your of your nodes. Okay, but then a single copy of the code for the nodes that just runs on the selected component of the environment state. Is that what you're saying?
Yeah.
Okay. Okay, that's my questions.
I've got two more questions if no one has a question. So, okay. So one is related to the structure of the proof. So maybe I didn't pay enough attention, but if I had to do the proof, I would probably try to have a sort of one validator and prove a standard validator and prove that this is correct, and then prove that the distributed validator implements or refines a validator, right? Because you already have a proof for one validator. It was designed in Coq, for instance, let's say by the runtime verification team. And in your own work, you said that it was parametric, your proof. So it holds for a 0 or 1 validator in the set. So I would have probably tried to have a proof showing that, assuming that I've got a validator that's honest and I've got a distributed validator, the two, let's say, notion of being honest, one was implied by the other, and have a refinement proof like that. So is it what you did or not?
No, that's not what we did. I mean, I don't think we could have used the work from runtime verification as the
So no, I don't mean reusing their work, but that's the proof engineering side, which is the structuring the proof, right? You're basically building a distributed validator to emulate a validator, but with more resilience. So I would expect to be able to prove it in a layered manner, saying, okay, I've got the proof for a validator, a single validator, assuming it's honest. And I'm going to show that if I've got a distributed validator and I have a notion of honest for distributed validators, it implies that the observable behavior of this set of validators implies that it's honest as if it was seen as a single validator. Because at the end of the day, you reconstruct the key at the end and everything, so it's equivalent to one validator. So that would make the proof probably easier to manage. And the second question I had is, so that's what Ron was alluded to as well. What are the assumptions? Because there's lots of things like in liveness and so on. What are you going to assume to prove liveness? What are you assuming in your proof at the moment about cryptographic primitives and so on?
Yeah, thank you. So for cryptographic primitives, essentially we assume that they're ideal, general, like hashes, that no collision. Threshold signature is correct. So if you have less than the shares, you can't reconstruct the signature. Unless the shares they sign the signature for the same data, you can't reconstruct it. So we don't assume any probabilistic behavior. We just assume that things work perfectly. As I said, then also for Byzantine nodes, we assume that they can't forge signatures. They can send basically messages signed by honest nodes unless they've already received them. And for liveness, which we haven't started yet, we plan to assume synchrony so that there is a known bound on the messages to be on the delay. Is there anything you'd like to add?
And yeah, thanks, Tom. And we also need to have an assumption on the speed of processes. We also assume that they are synchronous. Yeah. And yeah, I think for other assumptions, Roberto already mentioned.
Yeah, and for example, the one that Thanh-Hai showed in the axiom, we assume that uniqueness in the signature of the signature scheme, so that you can't have two different signatures for the same value of public key. There's another question from Ron.
Sorry, I'm done.
Okay, thank you.
Didn't lower my hand.
Yeah, thank you. Oh, well, there you go. That was a good talk. And thank you for getting to, I know it's a complicated thing putting a talk together, so very much appreciated. Yeah, so thank you. There are a whole heap of talks coming up in the coming weeks. In fact, next week's talk is by Babu Palal, which is about his thoughts on MEV. And then we've got Barnaby Monod, and he's going to talk a bit about our proposer builders. There's my talk on inline assembler. There's also another talk that is going to be on April the 12th, which is Philip from LeFi talking about his thoughts on why it's a good idea to have aggregators, and not just aggregators for value transfer for cross-chain, but aggregators for arbitrary message communications. So I think that should be interesting. And on May 3rd, Leo has called it Introduction to, but I think this is really going to be a deep dive into AMMs and really cover a broad spectrum of stuff. So that should be a very interesting talk. Yeah, so look, thank you again, Thanh-Hai and Roberto. That was really good. And yep, there's all the socials and stuff. I assume everyone knows by now, but if you don't, please join the meetup or watch this on YouTube. So anyway, thank you again, and see you all next week.
Thank you all for being here. Bye.
Bye-bye.
Thank you. Bye.